Hello. So this is the final part of this chapter of trigonometric ratios. So looking at sine, cos, and tan. And last time we looked at sketching the sine, cos, and tan graphs. And this time we're going to look at transforming them. So this is going to basically apply what we looked at in chapter 4 with graphs and transformations, where we looked at the transformations such as f of x plus a, where obviously that's it moved it right or left by a units. We looked at f of ax, where it stretched horizontally, basically meaning the x coordinates were like divided or multiplied by a, right? Then also we had af of x, where that multiplied the y coordinates by a, and also f of x plus a outside, which then added a to the y coordinates. So it basically shifted the graph up or down by a amounts. So that's basically what we're going to look at. And again, if you need a refresher on that, I recommend going back and looking at that video. But we'll basically be applying them transformations to our trig graphs. As a very brief reminder, these three trig graphs, the sine one for 360 degrees looks like that, and the cos graph looked like this to 360 there, and the tan graph looked like this. Okay, and so that's 180 degrees there, and then this is 270 and 90 for the asymptotes there. Okay, so that's the cos graph and the tan graph. And so essentially we will be applying these transformations to these three graphs. So as another very brief recap to these transformations, the whole philosophy is firstly what any transformation we do inside the function. So say if we did f of x plus a, you do the opposite to what you expect. Okay, if it's inside the function, you do the opposite to what you expect. Okay, so for example, let's take this graph here, the x squared graph. That's f of x, right? Say. Okay, if we then did f of x plus a, what would you expect? You'd add a to the x values, so the x coordinates, meaning it essentially shifts to the right by a. But it does the opposite, and actually you subtract a, so you're going to the left by a amount. So it's going to look something like that instead, where this is minus a there. If we then did f of x minus a, then we do the opposite again, and instead you add a, which would then obviously shift it to the right, and so that it would be a there. Okay, and so that's the general gist, right? And then likewise then, what we do outside the function, say if we had 2f of x, it does exactly what you do expect. Okay, so inside the function does the opposite, and what happens outside the function, you do exactly what you expect. So what you'd think is multiply 2 by f of x, so double the y coordinates, right? That's what you expect. So again, if we say had this same graph again there, so say if at 1 here, no, let's say at 2, let's say at when x is 2, this is 4, so that's x squared, right? Well then, if we double that, so if we do 2f of x, it would look like that, right? So now, when x is 2, now y would be 8, okay? So it would look, it would be up here somewhere. And so it's a lot more like stretched, compressed, because the y values are higher now. So now if this was 2, now this would be 8. So it does what you expect, right? You double all the y values. And that's essentially what we'll be doing, okay? That is essentially what we'll be doing. That's the key philosophy with these transformations. Inside the function, or inside what happens to x, you do the opposite. What happens to the y, or outside the function, you do exactly what you anticipate. So, okay, let's have a look at some examples then to put that into practice. Okay, this example, sketch on a separate set of axes the graph of firstly, y is 3 sine of x between these values, 0 and 360. So how I like to approach these questions, I just like to do the original graph first, right? So firstly, sine of x, as we just looked at earlier, that the sine graph looks like this, right? For 360 to 0, this is sine of x. Or I should say y is equal to sine of x. And here is 1, here's negative 1. You can label the graph if you want. That'd be 180 if you want to label it. But that's the whole idea, right? That's the sort of shape, right? Those are the key sort of points, right, of the graph. But then I want to do 3 sine of x. Well, if you imagine sine of x as f of x, right? Then 3 sine of x is effectively 3f of x. Well, then that means I'm timesing it. The 3 is outside the function, so it does what I expect. So we'll be multiplying by 3. And because it's outside the function, it affects the y values. So what I'm doing here is I'm going to multiply the y values by 3. Well, how I'm going to sketch that then? Well, it will still be between 0 and 360. But the key idea is with this is the y value will triple, right? That's what we expect, to multiply by 3. You could say more formally this would be a vertical stretch by scale factor 3. That's the formal sort of description of what we're doing, but essentially we're multiplying the y values by 3. So in that case then, well, the values here, 1 and minus 1, would basically now be 3 and minus 3 if they're times by 3. So now if 3 is up here, say, and minus 3 is down there, but then the new graph will look like this. So this will still be at 90, this will still be at 270, this will be at 180, and this will be at 360. So the x values remain where they are, it's just that the y values are tripled, okay? So the graph is a lot more like stretched up in a way, because it's a vertical stretch. But there we are then, so that's the graph then. So essentially, to indicate that, essentially you need to triple the y values here, so you get this graph. Okay, part B then says y is now equal to minus tan theta. So again, I'm going between minus 180 and 180. So let's sketch the original tan graph between them values. So if we just have tan of x between so firstly from 0 to 180, well, it's 0, it starts at 0, then it goes up, and then there's an asymptote at 90. Or theta is 90, I should say. And then obviously it goes back up again. But then this is 180. I don't need to go any further because remember, I only need to sketch between minus 180 and a positive 180. So my graph stops there on the right. And then if we go backwards then, the graph would go like this, and then there'd be an asymptote at minus 90. And then it shoot back up again like that. Okay, cool. And then that would be minus 180 there. So that's my graph, right? That is the original tan graph. So I should say this is y is tan theta. Alright, so that will help me, right, if I sketch the original graph. Then I'm going to apply this transformation, or because this is minus tan theta. So what do I expect will happen? Well, imagine if the function is tan theta, the minus is outside the expression. So it will affect the y values, and it does what I expect. I multiply all the y coordinates by negative 1. What that means is essentially the y values will flip signs, right? So I guess let's just consider a few different points on the graph. Firstly, the origin will stay where it is, because 0 times minus 1 is still 0. But then, well, think about it. The y values up here are positive. So it's going to have the sort of negative, the opposite effect, right? instead it's going to go downwards like that, right? So that part of the graph will then go down. The asymptote will still be at 90. But now it's going towards in downwards, right? 90. And then think about this part of the graph. This part of the graph is negative in the y-axis, so the negative y-axis. So it's going to, again, sort of go upwards. So it's going to go that way until it reaches the 0 there. So it's basically, hopefully you can see, the whole idea is because I'm times it by negative, I'm flipping the sign. So it's basically, hopefully you can spot, it's going to be a reflection in the x-axis or the theta axis, right? That's essentially what's going to happen here. So if I then do that, there we are, and then 180 is there, okay? But then what about this part, what about the left side on the negative part? Well, again, this part of the graph is negative on the y-axis, so it's going to again reflect upwards instead like that. So there we are. And again, it would then be an asymptote here at minus 90. And then again, this part of the graph will again sort of go on in the opposite direction. It would be down here, and it would look like that. So then, if we do that bit, there we are, until it reaches minus 180 there. And there we are, that's our graph, right? So there we are. So again, you could memorize this if it's minus f of x. As we saw here, it's essentially a reflection in the x-axis, or the theta axis in this case. But I don't. I mean, like I said, I just consider flipping the signs of the sign of the y parts, right? So if it's above the y-axis, in the positive y-axis like this part, it would then be on the negative like that. And then hopefully once you do that, you can spot what the graph will look like. So yeah. So there we are then. So that then be y is minus tan theta, which is what we want. Okay, cool. Let's have a look at another example. Sketch on a separate set of axes. The graphs are firstly y is minus 1 plus sine x. Right, so again, I'm just going to draw sine of x first. Between what, 0 and 360. So if I just do a little sketch, there we are. So that's y is just sine of x, and that'll be 360. That'll be 0 there. That'll be 1 there, minus 1 there. Okay, so that's the basic graph, but then I want minus 1 plus sine x. Well, this minus 1 is outside this function sine of x. So the minus 1 is outside, so we basically do what we expect, and we subtract 1 to the y values, right? So we're going down by 1, essentially. So with that in mind then, if basically every y value is going down by 1, well, firstly this 1 here, at the top here, would then go to 0 there. So with that in mind, at 90 it will then be there. At 0, here on the origin, it would then be at minus 1 if we're going down by 1. Oh, there we are. Again, at the origin here, it would be minus 1 there. If we're at minus 1 here, at the bottom here, it would then be a minus 2 down here. So if I make a note, minus 1 is there, minus 2, 0. And then obviously when it goes back to 0, it would then be at minus 1 there. So then if we sort of connect the dots, a new sine graph would look like that. Cool. So then that'd be 360, that'd be 180, that'd be 270, and then that'd be 0. So that's our sine graph then. So this is that if this is sine of x on the left side, that graph. Well, what we've done here is, in this right graph here, we basically subtracted 1. We went down by 1. Okay, so we subtracted 1 to the y coordinates because the minus 1 is outside. So we're essentially saying we're subtracting 1 to the y values, which is what we've done here. So then this would be minus 1 plus sine of x. And there we are. So we've got our graph there. Cool. Let me make this a bit clear. There we are, 90 there. The axis is a tad bit off, but it doesn't matter. As long as you've got the general sketch and you indicated the points, doesn't matter how sort of rough the sketch is. But there we are. Cool. And then part B then, we need to sketch y is a half plus cos x between 0 and 360 again. So again, my strategy is, let's just consider what cos x is, and then work from there, and then apply any transformations to that original graph. So if I then recall the general cos x graph to 360 degrees, it looks like this. Yep, okay, cool. And then that'd be 1 there and minus 1 there. Okay, so that's y is cos x, but then I want to add a half to it. So that's going to do what I expect, because it's outside the function, right? The function of x. So I'm going to add a half to the y coordinates. So all the y coordinates will be added to a half. That is basically shifting it up by a half, okay? So with that in mind then, well, firstly at 1 here, it's going to go to 1.5, which should be 3 over, or 1.5, right? We should be, say there. So it will start there, and then when it reaches 0 here, it will then be at 0.5 instead. So plot the point there, plot the point there. This next point at minus 1 would then be minus 0.5 if I add a half to it. So it would be down there. And then hopefully sort of spot then, this will be 0.5 as well. And then once we return back up to 1, it will then be 1.5 instead. So everything gets shifted up by a half, okay? So if I connect the points together, then I get this graph, okay? And then that is now a half plus cos of x between 0 and 360 degrees. Cool. So yeah, so that is my general sort of advice. And as you can see here, I considered a few points to see where they would have mapped to, and then I sort of sketched a graph and drew a curve between those points to help me sketch the whole curve. But yeah, okay. And if we wanted to be fancy again, remember we could also do, if they ever say to describe the transformation, remember when we looked at that in the earlier chapter, this would be a translation, a vertical translation. Vertical meaning basically the y-axis, right? So up and down. So vertical translation by a half, okay? Or no, I should say by a vertical translation a half units upwards. There we are. But there we are. So there we are. Okay. So now we've got these questions, and we are told to sketch firstly y is tan of theta add 45 degrees between 0 and 360 degrees. Now, our strategy is, first of all, we are going to sketch just the normal tan graph, and then we can see how to apply this transformation. However, the difference with this question is now, as you can see, we are changing the domain, right? We're changing, remember the domain is a fancy name for the input or the values of x, or theta in this case, of the function. We can see that because this 45 is inside the function, it's inside the tan, so it's going to affect the domain or the values of theta. What that means is then, we need to sketch for theta between 0 and 360, but that's for this function. When we are sketching the tan, just tan of theta, we need to be careful with the values of theta we pick, right? When the values we're sketching the tan graph from. What we're going to do then, essentially, is when we draw our tan graph, which again I highly recommend, so you can see what the transformation is. The values that we sketch it from won't be from 0 to 360, because again, that's the domain here for theta add 45. When we just have theta, What we're going to do then is, well, we're going to have, it's going to be between 0, theta and 360. We are basically going to copy the domain, right? What I mean is, we have theta add 45 here. We have theta. So basically what we're going to do is add 45 to every part of this inequality. So then we're going to get 0 add 45, and then theta add 45, and then 360 add 45. Right, and therefore then we get 45 between theta add 45 between 405 degrees. And so this is where we're going to be sketching our tan graph from, right? Okay, so we're not going to start at 0, we're going to start at 45. So it starts at, the tan graph starts at 0 here, at 0, right? That's not really going to start from 4. If you have an asymptote at 90, here, as we know, that's a tan graph, the asymptote is there. 45 is going to be in the middle, so it's going to be starting there, say, right? And then it's going to do that sort of asymptote behaviour, okay? And then we just continue the graph on from there, right? So that'll be 180 there. And then we're going to get another asymptote at 270. And then we're going to continue the graph. Now this would be 360 at this point, but we need to continue 45 degrees more because actually we need to end at 405, okay? So it'd be like that, right? So actually our end point would be 405 degrees there, okay? Okay. So this is the graph y is tan theta. So now why have I drawn this again? Well, like with the other questions, I can now apply this transformation to this graph. Because what's the transformation doing? We are saying we want, well, what we think is we want to add 45 to theta, or to like sort of the theta values, right? Meaning it would move 45 to the right, right? But we do the opposite because remember what happens inside the function, we do the opposite to what we expect. So actually we're going to go and subtract 45 instead, meaning we go to the left by 45. So the graph will shift to the left by 45 units. Well then, this is why we do this strategy, right? Because then, if we're then going to subtract 45, well then we're going to get 45 minus 0 here. No, 45 minus 45. And then theta add 45, take away 45. So again, we're subtracting 45 to everything. Because that's what we're going to be doing. Going to the left by 45, meaning we're subtracting 45 to every value of theta. But therefore, then we get 0. Theta add 45, take away 45 is theta. And then 405 take away 45 is 360. So actually, that's how we get the domain they want then. So that's why we do this that's why we copy the domain, right? Inside the function, right? We copy what's in the function because basically we do the opposite and we get back to the normal domain they want, the inputs that we want, right? The values of theta. So when we apply this transformation, then well, we're going to shift by 45 to the left, right? This graph here of tan theta. So if we do that then, well 45, if we're going to the left by 45, subtracting by 45, it's now going to start at 0. So it's going to start up here, because remember it's up here at 45. It has to be in the same position up on the y value, right? But anyway, it starts here at 0, and then it essentially goes up like that. And then it have an asymptote, not at 90 degrees now, it'll be at 45. And then we sort of do the same, right? You have the same sort of shape like this. There'll be an asymptote here. But the second asymptote was 270, but we need to subtract 45, right? So 270, take away 45 is 225. So this is where the asymptote's going to be. And then we copy the shape again. And there we are. And it ends at this point here. Sort of in the air, right? but there, okay, and that end point would no longer be 405, but it would indeed be 360, okay, and there we are then. Obviously, again, because 405 take away 45 is 360, and that is the graph between 0 and 360 then, and this is the graph y is tan of theta add 45, okay, between that range values of theta. So yeah, so it's the same sort of strategy then by you know, very helpful to consider the normal tan graph and then apply the transformation to it to see exactly what happens. But we need to consider the angles we're ranging from, which is the key difference here. So yeah, let's have a look at another example then. So now we have cos of theta minus 90. Oh, should say one more thing. If you really want to be precise, we probably should label the y-intercept here as well, if you wanted to. If you wanted to find this y-intercept at 0, well, that would be setting theta to 0. And then y would be tan of 0 add 45, which should be tan 45, which will get you 1, I believe. Yes. So at that point it'd be 1 on the y-axis there, okay, and theta would be there. Okay, so there we are then. And this point as well, when it meets the x-axis, well, originally it's 180, but 180 take away 45 would be 135 here, okay. There we are then. I just thought I'd fully label that graph. Sorry, apologies. Let's go back. Let's do the next part then. So we have cos of theta minus 90 degrees. And theta needs to be between minus 360 and positive 360. Right, so again, the strategy is then let's just firstly consider the cos graph on its own by default. But we need to work out the degrees we need to consider, because it won't be the normal cos graph we want would not be between these values, because that's for this function theta minus 90. When we're just drawing cos theta, well, we need to basically adjust the domain, right? Adjust that interval by just literally copying this. So theta minus 90, well, we have theta, so just take away 90 to everything. So then minus 360 minus 90 will be minus 450. And then we'd have theta minus 90. And then 360 take away 90 would be 270. And there we are. Cool. So these are the range of values we'll be drawing our cos graph from. So then, let's draw our axis then. Y here. Okay, so remember that the cos graph has this sort of shape then. But yeah. But we need to again recognise the range of values we're bounded by, right? So it only goes up to 270, not 360. So that part of the graph would look like this, and it ends here at 270. Okay, and then if you go backwards, then well, this would be minus 360 at this point because it's done a full wave, right? It's gone back to its starting point, right? But we need to go a bit further than that because we have minus 450, which is another 90. So actually it would then go like that, and then there we are. That's our end point. Cool. Okay. So then we just apply the transformation then. So this is again y is cos theta, but we want cos theta minus 90. So again, the philosophy is if it's inside the function or the bracket, we do the opposite to what we expect. Well, what do we expect? We subtract 90 to the theta, meaning we'd shift it to the left by 90. But no, we do the opposite, add 90, meaning it has to go to the right, because we're increasing by 90. So the whole graph's going to shift to the right by 90, okay? So if we do that then, we get this graph. So the shape of the graph will remain the same, it's just moving place. Okay, it's moving to the right. With that in mind then, well, At 0 here, it's at 1, right? This would be 1 here on the y value. But it's not at 0 anymore. It's not at 0. It'd be at 90. So it'd be at 1 at 90. And then the graph has the sort of same shape then from this point. So it would go downwards up there. And I need to extend my axis. Hang on, there we are. And it would also go backwards in the same way. There we are. Okay, so I'm just matching the shape of the graph, because the shape of the graph will be the same. It's just moved. So I know I mapped this point at 0 to the point at 90 here now, right? So this point here will now be here. Okay, and then from that I've just basically copied the shape of the graph. Okay, because that's what happens. But the points we're going to have now, well, it's at 0 there, but this will now be 360 because I'm adding 90 to 270 because that's what we're doing. So we get 360 at the end here, and here at this end will again be minus 360 because minus 450 adds 90 would be minus 360. And actually you can notice we're now between minus 360 and positive 360, which is what we wanted, right? That's what they told us. So that's the aim, right, of this sort of like adjusting for like the domain, right? When we're sketching, we just copy the, you know, the stuff we're given, essentially. Okay, I guess you could label this as 1 and minus 1 at the for the values there as well, but there we are. Okay, cool. And also this would be 180, and this would be minus 90, this would be minus 180, up here would be minus 270, and yeah, if you really wanted to label it, that's fine, and 270 there. But there we are. Okay. Okay, we've got this example then. Sketch on a separate set of axes. The graphs are firstly, y is sine of 2x. Again, between 0 and 360. So we're going to consider the sine graph just sine of x. But again, the problem is where we're sketching it to, what angles are we using? Because it's not going to be 0 and 360, because this would be for the function 2x. Remember, but because we're changing the domain, right, the values of x, because we have 2x and not x, we need to, again, adjust for that, okay, with this interval. So what I'm going to do then, well, I will have x here, but I need 2x, so I'm just going to times the whole inequality by 2. So if I times by 2 to both sides, like an equation, right? Well, 0 times 2 is just 0, then x times 2 is 2x, and 360 times 2 is 720. So that is the interval. That's the interval we will be sketching for the sine graph. So we're sketching from 0 to 720. So remember, the sine graph looks like this. Yes, obviously that'd be 360 here. So we need to do another wave to get to 720. There we are. Okay. So 720 will be there, and we start at 0, 1 and minus 1. So that would be y is sine of x. Okay. But now I want sine of 2x, right? So what does this do with sine of 2x? Well, again, because it's inside the function, inside the sine, we do the opposite to what we expect, meaning what we'd expect to do is double the x coordinates to times by 2, but we're going to do the opposite and divide by 2 instead. So we need to divide all the x values. Say here 360 would then have to go to 180, 720 here would have to go to 360, and so on. Okay, so if we do that, then if we just halve all the x coordinates divided by 2, if we draw our axis then, well, we're going to copy the graph, the shape of the graph, but we note that particularly 360 here would then be 180 if we divide by 2, so it'd be there, and 720 would then be 360 at the end here. Okay, so with that in mind then, we're going to have this sort of shape. There we are. Okay, cool. So there we are. So we have y is sine of 2x. So we just copied the shape of this graph basically, but I made sure to end it at 360 there. But you can see I got two sine waves, kind of like what I've got exactly up here, right? So that's the whole idea, right? I'm just matching the shape of the graph, but I'm just dividing the x coordinates by 2. Okay, so there we are then. So that's my graph. Then again, I could annotate it a bit more if I want to. This would be 90. There, this would be 45. This would be 135. This would be, well, that would be 270. That would be 315, I believe. Yep. And this would be 225. There. Okay, cool. So, and again, you can see we're shrinking basically the graph in half, right? Which makes sense because we're dividing all the x coordinates by 2, meaning we get 2 sine waves instead of 1 in the same interval, 360 there. Okay, there we are then. Okay, so then part B, we now have y is cos of theta over 3 between minus 540 and positive 540. So there we are. Okay, so again, let's just consider the normal cos graph, right? Cos theta. But where are we drawing it from? The degrees, the angles. Wow, it's not going to be minus 540 to 540 because that's for this graph of theta over 3. But I just want theta, so I need to adjust for that. So I need to match the domain I'm given, right? The input I actually have. Well, I have theta here. I want theta over 3. So to match that, well, I'm just going to divide everything by 3. So then if I do that then, by minus 540 over 3 gets me minus 180. And then we're going to have theta over 3, and then 540 over 3 would be positive 180 degrees. So that's what I'm going to be sketching from between minus 180 to 180 for the cos graph. Okay, so if I sort of draw my cos graph then. So again, the cos graph looks like this between 0 and 360, but I want to stop at 180. So actually, I need to stop here at 180 there. So if I sketch that part of the graph then, again, it's gonna look like that, okay? There we are. So it's 1 there, minus 1. And again, I'm going to do the same backwards. And there we are. So that'd be minus 180 there. That'd be 90 here, minus 90, sorry. And then positive 90 there. And there we are then. So that's our graph. So then we essentially need to then do theta cos. This would be y's cos theta then, between these values, minus 180 to 180. But then what I want to do is then sketch theta over 3. Okay. Because this is again the normal cos graph between these angles, but I want theta over 3 instead. So again, the rule is what I do inside the function, I do the opposite to what I expect. So what do I expect? Well, I expect to be dividing the thetas by 3, all the theta values by 3. But I'm going to do the opposite and instead multiply them all by 3 or triple them. Meaning that this 180 here and the minus at the end here, they need to be tripled. So 180, well, the triple that is indeed 540. Okay, so the graph needs to end at 540 instead of 180, and vice versa backwards as well. So if I draw my axis, so 540 would be about here, and then minus 540 back here. And so then I need to essentially, sort of copy the graph again. Also, it might help to say that 90, well, if I triple 90, it'd be 270. So that'd be about there. And then we're going to have minus 270 there. So then I just need to sort of like sketch the graph, right? To copy the shape of the graph, but between these values again. So I'm sort of going to be stretching it, right? Anyway, so it starts at 1 again. So it needs to level off at 270 now, not 90. So it's going to look a bit like this. And it's going to level off at 540. There. Cool. And then I'm going to do the same backwards to match the shape as well. Oh, it's a bit wonky, that is. There we are. Cool. There we are. There we are. Cool. So that would be what my graph looks like. And again, this would be 1 and this would be minus 1 down here. But there we are. Okay, so that's the graph of y is cos theta over 3. There. Okay, cool. And again, that'd be theta and this would be y. There we are then. So that's that graph then. So again, hopefully you got the idea now that we sort of adjust for the, you know, the adjusted domain or the range of values of x or theta or whatever by using what we're given in the function to mimic it, right? So we can adjust the range of values that way. So that's the whole idea then, right? But yeah. Okay, so tan x then, if I draw my graph, so again, between 0 and 360, well, it's at 0, it starts at 0 and then it shoots up towards the asymptote, and then that would be x is 90, and then it shoots back, and then it is sandwiched between the next asymptote, so 270 there, and then at 360, at the end here, it just shoots back to 0. There we are. Cool. And then that'd be 180 there, 0 there. Okay. And then we can do Then we can do it in reverse again. If we go backwards to negative, so it go like that. And then the next asymptote would be minus 90. There we are. And then the next asymptote would be minus 270. And then it would there we are, and then it would shoot to 0 there at minus 360. So that's my whole graph then between minus 360 and 360. Right, okay, but then I need to sketch tan of minus x, right, if I make that clear. So what would you expect to do inside the bracket then? Well, because it's minus x, we effectively times it by minus 1. So you'd expect it to times by minus 1, the x values. But instead we do the opposite and divide by minus 1. Well, actually, in that case, dividing and times it by minus 1 is the same, right? So effectively, you can just think of it as times an x by the x values are basically multiplied by minus 1, meaning the x values basically switch sign, right? So the positive x values become the negative and vice versa. Right, okay. So how are we going to do that then? So firstly, again, to help with this, let's just consider a few points to consider. Well, firstly, at 0, it would still be at 0 because minus 0 times minus 1 is still 0. Okay, then at 180, it would still be, well, 180 would then be minus 180, but still be at 0, so it would be over here. And then 360, well, it'd be minus 360 if you make it negative, so minus 360 would be over here at 0. Right, okay. But the asymptotes, okay, let's consider the asymptotes, that might help. Well, x is 90 would go to minus 90. Well, actually, we already have an asymptote of minus 90, so we don't need to do anything. So we can already add an asymptote of minus 90 if we make that negative. So 90 is the negative of that's minus 90. Likewise, with the other asymptote of 270, well, the negative of that is minus 270. Well, actually, we've already got that asymptote, so it'd be in the middle here. And there we are. Okay, okay, then what about, say, 45 degrees then? 45 in the middle here. right? It'd be there. Well, 45 would go to minus 45, right? So it'd be 45 would be there. Is the asymptote a bit close to the axis? Nah. Minus 45 then, instead of positive 45 for x, but it'd still be at the positive y axis, so it'd be up here, right? If we just move it along, right, along the y axis, because it has the same y value, it would then be there. Likewise, this point here, if we it would be there somewhere. If we then take that point on this curve, it would then move across to there, because then x values are switching signs, so it would look like this. So essentially, then hopefully you can see it would look like that, and hopefully you can also see by doing this, it's a reflection in the y-axis. Essentially, we are basically going to be reflecting this curve in the y-axis. Right. Okay. So then, so we sketched that part. What about the next part? What about these points then? So, this would be 200. What would be in the middle there? 180. 180 had 45. 225. Okay. Well, if we reflect it in the y-axis, well, this part then would look look like this, right? There we are. So it'd shoot upwards instead, and then it would reflect up like this, and then there we are. And then the last part would look like this instead. If it's reflecting in the y-axis here, that's where it would look like. Okay. And then we could do, and then we hopefully sort of spot the pattern of the graph, right? So at this point, so if we continue the graph downwards, the asymptote would then be at 90 here, and then it would, and then it had this sort of shape until the next asymptote at 270, and then it would go downwards until 360 there. Okay. And so there we are. We've got our graph of y is tan of minus x. Probably the trickiest one actually. Again, hopefully you notice I plotted a few points to see what would happen, and what I spotted happened was eventually with these three. If I draw my original curve again, well, this point here, if it's positive 45, it would then because of the x value become the negative, we're basically moving it along the y-axis like this. Then this point would move to there, that point moved to there, and then I spotted the idea was it would be a reflection along the y-axis. So then I reflected the whole graph along the y-axis, but it can be quite tricky to spot exactly how it reflects. So even I had a little bit of an issue there. But yeah, eventually that's what the graph should look like when reflect the whole thing in the y-axis. Okay, and like I said, once you've got an idea of one part of the curve, you can the rest of the curve will look pretty similar. So then I just did that. But there we are then. So that's the graph then. Okay. Okay, so we've got this question then. We are told the graph shows the curve with equation y is sine x plus k between minus 360 and 360. And then it says for part A, find one possible value of k. Okay, so again, we have a transformation, right, of sine x plus k. Let's think about what that means then. Well, if we have y sine x plus k, again, this plus k is inside the function, inside the sine, meaning we do the opposite to what we expect. Okay, so what do we expect? We expect to add k to the values of x, meaning we're going to shift it to the right by k units. But we do the opposite and instead subtract k, meaning we're going to go to the left by k units. So it's going to be shifting the sine graph left by k units. Now again, with the other questions, it might be helpful to consider the original sine graph, right? So if we have just sine of x, now again we would need to adjust for the angle. So we'd have again minus 360 to x to 360, and then we need to add k. So it'd be minus 360 add k to all sides. So this would actually be technically what we need to consider for the normal sine graph. But I think with this question we only need I don't think we need to get too bogged down by it, because we just need to see what the sine graph looks like, right? We just need a good idea what it looks like. I'm not worried about the specific numbers, so let's just sketch between these values, right? Let's kind of sketch the sort of the graph we got up here. Anyway, so if we go from minus 360 to 360 of sine x, it would again the standard sine graph, 360 there. And then minus 360 there. 1 and minus 1. So this is why it's sine x. Okay, so now that we have our original sine curve again, and again, link it back to what we just talked about, this x plus k is basically shifting the curve left or right, depending on if k is negative, but it's shifting left or right. Now this is the shifted curve of this curve we're given is the shift of the original sine curve. But then what exactly is it shifted by? Well, this is where we need to sort of pay attention, because let's consider this point on the origin, right? On this sine graph. Well, this is at 0, but it's on the axis. On the x-axis, meaning if we were to just shift the graph left or right, this point could then be on that point, or that point, or that point, or down here. If we're shifting it left or right, that point on the axis would still have to be on the axis if all we're doing is moving the curve left or right. Meaning then that this curve at that point then, again there, has to either match that point, that point, that point, or that point on that shit translated curve. Because those are the points where it passes through that is on the axis as well, okay? So the origin could only map to one of these 4 points, right? So we're going to consider them, okay? So firstly, let's consider this minus 60, closest, right? This 60 here. So then what we're going to do then? How are we going to get from the 0 to minus 60? Well, hopefully you recognise the curve here we're given is shifted 60 to the left, right? Now what we're going to then consider then is, if I get another colour, it's shifting our original sine curve to the left by 60. Now hopefully it matches the curve we're given, right? So if we shift it to the left by 60, it would be about that origin point would be about there. This point up here would probably be like there somewhere. This point here would probably be about there. And so then if we sort of connect the curve then, if we shift this original sine curve by 60, it would look something like this. There we are. Obviously we could continue it on, we could continue if we want to, but now actually notice this blue curve then, the blue curve which is shifting the sine curve by 60 to the left, doesn't that now pretty much bang on match the shape of the curve we're given? I think it does, yes. Well then therefore then that is a valid transformation then. If we shift the original sine curve by 60 to the left, we get this curve here. So therefore, that is a transformation that could happen then. So I'll make a note that we shifted to the left by 60 there. And now the blue curve matches the curve we're given, right? So then we can say that the curve... Let's get it in black. Oh. We could shift the curve, so the sine curve could be shifted, or technically we call it a translated, 60 units to the left. To get the curve y is equal to sine x plus k, which is the curve they're giving us, right? Remember, this is sine x plus k there. Right, right, okay. Well, therefore then, again, then we just define the equation then, sine of x plus k. If we moved it to the left by 60, meaning we'd have to subtract 60 to x, inside the bracket, inside the function here, we do the opposite. And instead of subtracting 60, we add 60. So therefore, we're going to get y is equal to sine x plus 60. And therefore then, k equals 60 if we just compare it. Okay, so there we are then. Part B then says, is there more than one possible value to your answer in part A? Give a reason for your answer. Okay, so if I get rid of this curve then. Okay, there we are. So, again, it's going back to what we were talking about earlier when I circled these points there. These 4 points are the only points given now on the x-axis, right? Therefore, those are the only 4 points where this origin could go to, right? If you move that sine curve, that point on the origin that's circled left or right, it could only fall to one of these 4 points potentially, okay? Because they're also on the axis. So we've already discussed about minus 60, so we don't need to consider that. But what about then if we shifted it to get to this 120 here, right? If I did that then, this 120, and let's do it in blue again. Well, how am I going to move this point at 0 to the point now at 120? We're going to have to move it to the right by 120, aren't I? So if I move this original sine curve 120 to the right, well, this point on the origin would map to about there, right? Given that obviously 90 would be there at the top of the hump. And then this point here, 90, would then go to about there. And so then if we sort of connect a curve in that case, so now if we start at this point 120, not at 0, the sine curve moved to the right now looks like this. Okay, and obviously we can continue it on. But let's have a look then. Does that match the curve we're given? No, not really. Well, the thing that stands out, for example, at this point, it's below the axis, right? When we move away from 0, it falls below the axis, but the curve in actuality is above the axis, right? So we've got this sort of shape where like it's going down like this. So it doesn't. This blue curve doesn't match the shape at all, right? The curve we're given. So we cannot translate the curve or move it 120 to the right, the original sine curve, to get this curve. So 120 to the right is not a valid transformation here, okay? Because the shapes do not match, okay? So it can't be 120 then. That point we cannot move it to 120, the graph. Okay, so then let's consider the other point then, 300, right? So again, how am I then going to get from the origin then to this point on the axis at 300? Well, I'm going to need to move it to the right by 300 then, aren't I? just move the origin at 0 to 300 there. So if I move it to 300, that point is now going to be about there, say. Then 90 would probably be about there somewhere. So if I then draw the graph in that case, starting at 300 now and not 0, it would then look like this. And if I just continue the curve on, oh hang on, it's a bit messy. There we are, something like that. Okay, and actually, hopefully you can see the graphs match then between the translated curve we're given and the curve we've done in blue. And so the graphs match then, right? So that means translating or shifting the graph 300 to the right indeed is valid, because then we do get this curve as well. Okay, so shifting the original sine curve 300 to the right will get me also the same curve given there. Okay, so that's another possibility then. So we could also another possible transformation is translating, which again just means shifting left or right, the sine curve, which again is the curve in black that I've drawn there. That's the original curve. The sine curve 300 to the right, units to the right, to also get the same curve given in the question, which was sine of x plus k, right? And there we are then. Well, therefore then, well again, if we're shifting it or moving it to the right by 300, well, when we put it inside the bracket here, it has to do the opposite. And moving to the right by 300 means we're adding 300 to x. So we can do the opposite and subtract 300, meaning y is going to be sine of x minus 300. And therefore k is minus 300, meaning there's more than one value of k. Because that's what the question's saying, right? Is there more than one possible answer to part A, given a reason for your answer? So yeah, so it could also be 300 to the right, to get the same curve as we discussed there. Okay, cool. So we are told the variation in the depth of water in a rock pool can be modelled using the function y sine of 30t degrees, where t is time in hours. Now I always underline with these sort of modelling real life questions the units and depth there, the units, and so time is hours and 0 between t and 6. First of all, sketch the function in the given interval. So again, we need to sketch y sine of 30t between 0, t and 6. So again, this is a transformation. We have 30 lots of t, not just t. So again, to help us with that transformation, to sketch it, well, let's just sketch the normal sine curve side of t, right? But we're not going to be sketching between 0 and 6 degrees. Instead, we need to again adjust, because the domain is changed, so or the range of values of t, will change. So then instead of t, we want 30t to match the domain given, to match the input of the function we're given. So how are we going to get from t to 30t? Well, we're going to times by 30, right? The whole inequality by 30. Well, 0 times 30 is 0, then t times 30 is 30t, and 6 times 30 is 180. Okay, so that's a lot more sensible, right? So we times by 30 there. So we're going to sketch between 0 and 180 the sine curve, right? So again, the sine curve looks like this, but obviously that's 360, and this will be 180. So actually we just want this part of the graph, the first half, right? So there we are, okay? And that'd be 0 there, and that'd be 90 at the top there, and 1 there. -1. So that is, well, that's the sine of x, right, or sine of t. but I want sine of 3t, not sine of t. So again, let's think about what this transformation is doing then. Well, again, because inside the function, the bracket, we do the opposite to what we expect. What do we expect? Well, we expect to multiply all the t values by 30, but we do the opposite and instead divide them by 30. Meaning that this 180, well, if we divide it by 30, I'll get 6, which is up there. So we need to end the graph at 6. And so, yeah, that's really it. So if we copy the shape of the graph then, and then we end at 6 now. There we are. It'd be 6 there, 0 there. And again, in the middle, it'd be 3. Obviously, you can see that because it's symmetrical in the middle, it'd be halfway. But also, 90 divided by 30 is indeed 3. So there we are then. So this would then be the graph sine of 30t. Cool. So that's part A done. And that's, again, between 0, t and 6. Cool. And then part B then says, if t equals 0 represents midday, during what times will the rock pool be at least half full? Right, so first of all, midday as a time, that's 12 p.m, right? Sometimes they will expect you to work with, you know, times like that in PMs or hours or AM or something like that. But that's 12 p.m, that's midday or noon, right? And it says, during what times will the rock pool be at least half full? So the depth is the curve, right? That's the sine curve. It's talking about the depth here. That's what we're measuring. So the depth has to be at least half full. Well, again, the maximum value is 1 of the sine curve, right? So half full, halfway, would actually be 0.5. So if we draw the line of 0.5, right? Actually, I'm going to redraw the curve again and not make it too messy. There we are. 6, 3, 0. So 1 will be at the top then. The 0.5 would be in the middle. So if I were to draw that line then, and that would be effectively saying y is 0.5. Now, 0.5 then, again, would have two solutions then, two intersections with the curve there and there. What we effectively want then is to solve it, right? We want to find these 2 points there and there for these intersections. And then actually, when it's at least half full, well, it's half full between these 2 times, right? That's the gap when it's above that half full time, right? So we just want to find these 2 points then, essentially. The values of t, or the angle, or whatever, where the two intersections happen. So how are we going to find that then? Firstly then, this 0.5, this is effectively solving the equation sine, because our curve is 30 sine of 30t, we have to equate that to 0.5, right? Well then if you do inverse sine, so then our angle 30t would be inverse sine of 0.5. If I do that on a calculator, I get 30 degrees, right? Well, that same 30t has to equal 30 degrees, so therefore t, if I divide by 30, t is 1, right? Or 1 degree. But t is 1, so actually this is saying then, the calculator will always give you the closest point to 0. In other words, that point there. Well, if t is 1 there, there we are. So we get 1 there. Okay, but then what about this other point then? Well, this is where we then need to consider the curve, right? This second point there, because of the symmetry of the curve. And again, we kind of looked at cases like this with the ambiguous case with the sine rule earlier on in the chapter. But the idea is with the symmetry of the curve. Well, at both ends of the curve, so between 0 and 1 here, and at the end here at 6, the gaps will be the same, right? So the gap between 0 and 1 at the start here is 1, right? And so therefore that gap also has to be 1. Now, we end at 6, and we want to go to the left by 1, right, to get to this point here. Well, then 6 take away 1 is 5. So that's the other solution then. So therefore we're going to get t's 1 or t's 5 are the solutions then, right? They're the solutions to sine of 30t is 0.5. Well, there we are then. So the times when you know the depth is half full, or in other words when the curve is above 0.5, so above halfway, well, it's between these two values of t then. So it's between t's 1 and t's 5. But then this is where we need to pay attention to the units in the question, because it's asking about the times, right? So not just the values of t, but the times, right? So this is where we need to pay attention to this. It said at t0 it's midday, so we start at midday at 12 p.m. Now t's in hours, so we got between t's 1 and t's 5, right? Well, when t's 1, that's an hour after 12 p.m, so that'll then be 1 p.m, right? Likewise, when it's 5, it's going to be 5 p.m, right? 5 hours after 12, right? So those are the times then, right? Between those values of t, between 1 p.m and 5 p.m. So therefore, what was it? The depth, was it? The rock pool, okay. The rock pool is half full, is at least half full. Between 1 and 5 p.m. And there we are. So that's the question then. So yeah, I would say that can be quite difficult seeing a question like that for the first time. We will look at loads more examples in the next chapter when we look at solving equations like this, solving, you know, in this way where we were finding the angle and using the graph to find all the solutions. We will look at loads more questions like this. So don't be freaked out if it's quite tricky. We will look at loads more examples like this in the next chapter. But yeah, so that's that question then. Okay, let's finish off this exam question, which I don't think is as bad. Okay, it might look bad, but I don't think it is. Right, okay, so we are given a part of the curve with equation y is 3 cos of x. The point P, which is there, is a minimum on the curve, with C being the smallest negative value of x, which the minimum occurs. First of all, state the value of C and D, so the coordinates of C and D. There. So again, it's a sort of transformation, right? We have 3 cos of x, where again, it can be handy to consider, firstly, what cos of x is, right? The shape of cos of x. If you draw the shape cos of x, it will look like this. And then that would be 360, and that'd be 0, and that'd be no, sorry, yeah, this would be if I extend it, this would be 360, and then minus 360 would be there, okay, and also the values of 1 and minus 1. So again, hopefully you can sort of realise then that this point here at the bottom of the bottom of the curve at this point here, that's going to coincide with this bottom of the curve here. But hopefully you can see, well, this is going to be minus 180, right? So this point is when x is minus 180, y is minus 1. That's the minimum point there. So that's that's for cos of x, right? What the equation is 3 cos of x, right? So basically what we need to do is this minus 180 to minus 1, because obviously that is what it's that point, right? Hopefully you can spot that by how the shape of the graph is resembles. this minus 100, minus 180 to minus 1, well, we need to apply 3 cos of x. Well, the 3 is outside of the function, the cos. So it affects the y value, and it does what we expect. What we would expect to do is we'd multiply by 3. So the y value would be multiplied by 3, right? So then we basically need to take this point then and multiply the y part by 3 to then get minus 180 and then minus 3, right? You could alternatively, if you're struggling to visualise that, you could just literally sketch y is cos of 3 cos of x, right? If I did that instead, again, well, because again it would only be the y values being tripled, right? So instead of 1, it would then start at 3, and then it would have the same sort of curve, likewise down here, and then also it would go down at minus 3 instead of minus 1, because then this would be 3 cos of x. So the y values are tripled. Well, then this point then, well, it would still be minus 180, but then this new point would be minus 180 minus 3. Well, there we are then. So we do get the same point either way. But with single points like this, it's helpful to just map the point, right? So again, what you'd expect to do is times the y value by 3, because the 3 is outside the curve, meaning it affects the y value, the y part. So we triple the y part, the y coordinate. So minus 180 for x will stay there. And minus 1, triple that, we get minus 3. Therefore then, we can say that P, that point, is minus 180 minus 3. But then therefore then, the CD of C is minus 180. And D is minus 3. There we are then, okay. It was only 1 mark, so yeah, so you just needed to state that. So for the first part, in part B, we need to transform that point to now 3 cos of x over 4. X is in degrees. But okay, we need to then map this point P here. Remember, P was, if I write it again, minus 180 minus 3 in degrees there. I need to map P to this new curve, right? This new function, 3 cos of x over 4. So the original curve that P was on, if you remember, P was on the curve 3 cos of x, right? So I'll make a little note here, that original curve y is 3 cos of x, but now I've got 3 cos of x over 4. So hopefully you notice the difference here is now inside the function I've got x over 4, right? Well, again, what I do inside the function, I do the opposite to what I expect. What do I expect here? Well, x over 4, you'd expect to divide the x value by 4. But I'm going to do the opposite and instead multiply x by 4 instead. So that's what I'm going to do then. I'm going to multiply the x coordinate of this by 4. If I do that then, if I multiply the x part, this minus 180 by 4, well, minus 180 times 4 is minus 720. And it will still be minus 3 for y. And there we are. So that's my point then. So therefore P maps to minus 720 minus 3 there. Cool, there we are. Then the next part is I now have y is now 3 cos of x minus 36 degrees. So again, originally it's 3 cos of x, that's what the point P was on. But now I need to map and transform P with this new curve. But again, the difference is I have x minus 36, right? Again, what I do inside the function, I do the opposite to what I expect. What do I expect here? I need to add 30, no, I need to minus 36 to x. But actually I'm going to do the opposite and add 36 to x instead. So So if I take the original P coordinate then, which was minus 180 minus 3, I then need to add 36 to the x. So minus 180, add 36, I get minus 144 degrees, and then minus 3 for y again. The y part is unchanged because I'm not changing anything outside the function. It's still 3. Okay, so there we are then. So that's the point then. So there we are. So therefore P maps to this point, minus 144 degrees, minus 3. And there we are then. That's it. So again, you do really need to remember how we transform stuff. Again, I did videos on that in the chapter 4. When we looked at graphs and transformations, we looked at how to do all these transformations with various examples. But hopefully you can now apply it to the trig graphs, right? But it's the same idea, the exact same fundamental idea being what you do inside the function. So if we change the x part, say like x plus 45 degrees, why we do the opposite, because you'd expect to move to the right by 45 because we add 45 to x, but instead, we do the opposite and go to the left by 45. And it's the same philosophy, right, which we looked at earlier on in the course. Likewise, as for outside the function, we do exactly what we do expect. So then if we did f of x, then plus 45, but then we do what we expect and add 45 upwards, okay, because that affects the y part. So y would move up by 45. But there we are then. So that's this chapter over with. So hopefully you can now be more comfortable with the trig graphs. But yeah, so that's it. I'll see you next time.